This work demonstrates a 5-actuator piezoelectric soft robot capable of complex motions. We develop a scalable simulation framework and explore complex dynamic motions. The robot consists of 5 piezoelectric actuators bonded to a single steel foil. We attach high-friction films on the underside at the two ends.
Each actuator will bend up or down depending on the applied voltages.
We develop a simulation framework of the robot to model a piezoelectric actuator as multiple motor link elements.
The motor link model is then integrated into a physics-based rigid robot simulator Piezoelectric to solve dynamics including effects of gravity and friction. The equations for the parameters can all be derived analytically. In our link torque model, each motor's torque is proportional to the difference between the joint and the target angles. The coefficient representing stiffness is inversely proportional to the link length, and the target angle representing the piezo effect is proportional to the applied voltage.
This simulation framework is validated against experiments. It is first tested in a single actuator cantilever. Experiment and simulation results are played at the same time for comparison. Good agreement is observed in time and frequency domains.
The actuator bends down and up with swaying voltage. We plot oscillation amplitude at varying driving frequencies. The resonant peak amplitude is 60 mm at 23 Hz. Moreover, the robot jumps in place when the middle 3 actuators are cycled at 14 Hz.
Again demonstrating close agreement between experiments and simulations.
The robot jumps completely off the ground. We plot the jumping head sweeping the driving frequency. The robot starts to jump at 5 Hz, and the jumping head maximizes at 14 Hz for 7.5 mm.
We further explore robot horizontal motion by changing the voltage waveform. A forward leaping motion is observed at 13 Hz.
The model reproduces the very complex behavior of the robot. Sweeping the driving frequency changes the direction of motion. The simulator shows good qualitative agreement with experiments. It captures forward motion at less than 3 Hz. The robot moves to the other direction at 8 Hz. Highest velocity is at 14 Hz. With the understanding, we design and demonstrate a wirelessly controlled battery-powered and tethered version of the robot. The flexible power converters on the top provide 300 volts and 1500 volts from battery-powered 7.4 volts. In addition, a Bluetooth microcontroller is connected for wireless control. Driven with different frequencies, the robot can crawl rightward, leftward, in-place rotate, and turn while crawling. In conclusion, we develop a simulation framework that can model static and dynamic behaviors of planar piezo soft robots. The simulator is validated by experiments including oscillation, jumping, and leaping. We further develop a wirelessly controlled and tethered version capable of bidirectional crawling, rotation, and turning. Future work includes further understanding and optimization of the complex motions.